Today's topic is friction. The definition for friction is the contact force that acts to oppose or reduce the sliding motion between surfaces. The N right here is to remind you that it's measured in newtons, and then I put a little asterisk to remind you that the direction of friction is always opposite to the direction of motion. And then remember, we also talked about friction being parallel to the surface as well. In your notes right here, you have a typical scenario of an object being dragged along a horizontal surface with friction. So what we're going to do is draw a free body diagram and look at the forces in more detail. You should know that the weight or the gravitational force is the one that's pointing downward, and I'm going to use both notations. Remember, force, the F with the subscript of a G, is gravitational force, and it's also called the weight, so you can choose whichever one of those two notations you prefer. For our next force, the normal force, it's the one that's perpendicular to the surface, so that one would be the one pointing up in this case, because as you can tell, it is at a right angle to our horizontal surface. Now, you weren't instructed on which way the force is being applied, so you can choose left or right. I'm just going to say that the applied force is moving in this direction, which would make our frictional force pointing in the opposite way. Remember that force can be denoted as a capital F with the subscript of an F, or a lowercase f by itself. Again, it's your choice on that notation. So what we're going to do is break these forces down into the vertical forces and the horizontal forces and talk about them separately. In your notes, you should see your page divided into two sections, horizontal and vertical. So we're going to examine the vertical forces first. You should recognize that the normal force and the gravitational force, or the weight, are the vertical forces in this scenario. I put an equal sign between them because the magnitude of these two forces are going to be the same for the situation that you were given. That is, an object being dragged along a horizontal surface with friction. So in this case, we can say that these two forces cancel each other out, or that they are balanced. And remember that this is only going to occur when the object is moving on a perfectly horizontal surface. So as long as your object is being dragged along a horizontal surface, we can say that the normal force and the weight have the same magnitude. What that means is that when we get to the equations and the math portion of friction, we can substitute one force for the other in terms of the number that we're going to plug in. Go ahead and pause the video if you need more time to write, as I'm going to move on and talk about the horizontal forces. In our scenario, the two horizontal forces were the applied and the friction. And remember, friction, you can do a lowercase f or a capital F with a subscript. It's your choice. Notice that I put a greater than or equal sign between these two forces, so we're going to talk about each of those individually. If the applied force is greater than friction, then that means these forces are balanced and we have no acceleration. Remember from Newton's first law that this has two meanings. The object is either at rest or it's moving with a constant velocity. So this would be like something that's sitting on, let's say, a piece of paper, and I drag that paper and the object stays with it. The object is moving at a constant velocity and there's so much friction there that it stays with that paper as I drag it. Our other option would be to make the applied force greater than friction, such that we unbalance the forces and there would be a net force. This means that we have an acceleration not equal to 0. So this would be like the magician's tablecloth trick, is if I was able to pull the tablecloth out from underneath the dishes and I applied such a large applied force that it was greater than friction, I unbalanced those forces and I caused the tablecloth to actually accelerate out from underneath the dishes. And this would be an example of Newton's second law. So when we get to the equations where friction is going to be important, we can either have one of two cases. Newton's first law, where the applied force and the friction are balanced, and typically you'll see that as your object moving with a constant velocity, or we can unbalance those forces and have an acceleration, which would be an example of Newton's second law. So let's say we look at these horizontal forces in a little bit more detail. If I apply Newton's second law, that was the equation F equals ma, And the force is actually the vector sum, because remember technically it was the net force, and that's called the resultant. So all of the forces acting on the mass is the net force, and we could write that as our equation of F net equals ma. This should be a review for you. We do apply Newton's second law to both vertical and horizontal motion separately, but since in this case our friction is horizontal, we're only going to look at the horizontal forces. The net force, or the resultant of my horizontal forces, would be to add the applied force vector plus the frictional force vector. And you can read along. Since my friction and applied force are in opposite directions, one of the ways we can denote that is by using the plus and the minus signs. And I tried to highlight on my copy. I'm not sure it turned out very well, so I'm going to rewrite this, and I'm going to take away the vector notation and say that my net force is equal to a positive applied force, and then I'm going to subtract a frictional force. I'm using the plus and the minus signs to indicate the different directions. So now if I substitute that in for Newton's second law, which is right here, I would say my positive applied force minus my frictional force, that's my F net, that total is going to equal mass times acceleration. This is Newton's second law. F net would be looking at the forces combined together, and then the total of that would equal mass times acceleration. So what I want to do is solve for the frictional force. If I were to rearrange that, and I'm going to go back and change this notation so that it stays consistent, my frictional force would be equal to the applied force minus mass times acceleration. And I want you to notice that if I had zero acceleration, then I would be subtracting off 0, and that whole mass times acceleration term right here would go away, and my friction and my applied force would be equal. But as long as I have an acceleration, I'm going to end up subtracting off applied force minus mass times acceleration to calculate my friction. Next, we're going to talk about one more characteristic about friction, and that term is called the coefficient of friction. Now, I don't have an actual definition for you, but one way you can think about the coefficient of friction is it's a property to describe the texture of a surface. In other words, it's a number that will tell us how rough or smooth a surface is. So again, that's not an official definition, but it is a way for you to think about coefficient of friction and what it represents. In our formulas, it's going to be denoted by the symbol mu. It's the lowercase Greek letter, and yes, it is the same symbol that we used for micro. However, those will not be in the same chapter, so you don't have to worry about getting them confused. When you see mu in our dynamics chapters, it is going to refer to this property called coefficient of friction. It is a number with no units, so that's going to be helpful as well. Another thing that you'll want to take note of is that when you are calculating your coefficient of friction, you should be getting a number between 0 and 1. The closer to 0 means that our texture is a smooth surface and has very little friction, and the closer to 1 would mean a rougher surface, and that would give a lot of friction. There are actually two different types of coefficient of friction, and we had a preview of this when we talked about free body diagrams. Those two types are static and kinetic. So you can tell the difference between them. If you wanted to denote which one is static and kinetic, you could use the S and the K for subscripts. However, they are both mathematically going to be the same, so this isn't necessary. That would just be a helpful tool for you. If we are talking about the coefficient of static friction, that means that the object is still, and it refers to before it would start moving. If we are talking about kinetic friction, that refers to movement. So when I ask you this question on which one is larger, I want you to think about what requires more force. Would it take more effort to make something start moving if it's still, or would it require more force to keep it in motion once you've made it start moving? I hope that you can tell that it would be much easier to keep something moving, which means it's going to require a larger force to start something in motion before it moves. So that's going to tell us that the coefficient of static friction is larger than the coefficient of kinetic friction. Mathematically, these will be the same equation, whether it's static or kinetic. And so what you're going to do is take the frictional force, and you're going to set it equal to the coefficient times the normal force. I have some example problems and we're going to apply these equations that we've learned today. For our first problem, you are asked to find how much force is needed to keep a 1,300 kilogram car moving at a constant velocity on a level concrete road which has a coefficient of friction of 0.04. It's always helpful to draw a free body diagram, so we're going to do that first. That would be our car. We know that the gravitational force is pointing down, and because it's on a level concrete road, that lets us know that it's a horizontal surface. This means, remember from earlier, that our normal force and our gravitational force, or the weight, are going to have the same magnitude. And then we are applying a force in one direction, and we know that friction is going to act against us because you were given a coefficient of friction value. So let's start with the normal force and the weight. We know that those two are going to be the same, so let's go ahead and figure out how much the weight is so that we can have a number to use in our equation for later. The gravitational force in this case is going to have the same magnitude as the normal force because it's on a level road, and the way that we calculate the gravitational force is to multiply mass times gravity. So let's go ahead and plug those numbers in and get a value. When we multiply those two together, that's going to allow us to plug in a value for the normal force of 12,740 newtons. The other thing that is important in the context of the problem is that it says constant velocity. So remember what that means for our horizontal forces. If it says constant velocity, that lets us know that the applied force and the friction are going to have the same magnitude. So that means if we are asked to find the applied force, mathematically, we can solve for the frictional force in an equation. And the equation that we have that involves coefficient of friction looks like this. The frictional force is equal to the coefficient times the normal force. So remember, we have some mathematical tricks. Because it's a constant velocity, we can plug in the applied force and the friction. That's where we're going to be looking for. This is the number we want to know. The coefficient was given, and then we calculated the normal force. Because it was on a level concrete road, gravitational force and normal force are the same number, and we found that by finding the weight of the object, which would be to take its mass in kilograms and multiply by 9.8. So remember, applied force and frictional force are going to have the same magnitude, so I can put that number in at the beginning over here in my equation. The coefficient of friction given was 0.04, and then we found our normal force by finding the weight of the object, and that number was 12,740 newtons. So all we have to do is multiply those two numbers together, and we find that we would need an applied force of approximately 510 newtons to keep that car moving at a constant velocity. This is about the time that our normal video lessons would stop. However, I do think it would be beneficial for you to go ahead and hang in there with me for a few minutes longer, and let's do these next two example problems together. You can read the question yourself. We're going to exert a force of 14 newtons, so I'm going to go ahead and label that on my free body diagram. And I know that I need to keep the block moving at a constant velocity, and I was also given the weight of the object. And then I'm going to fill in the rest of my free body diagram with my other two forces. This time we're looking for the coefficient of friction. So I'm going to change screens and we're going to work this problem together. So I've listed everything that's given. Remember that gravitational force and weight are the same thing. You can use either notation. And I also wrote in another piece of information that the acceleration is 0 because we have constant velocity, and we're looking for coefficient of friction. So a couple of things that I want you to take note of would be, because we have 0 acceleration, this allows me to plug in the same number for the applied force and the frictional force. And then also, because we're on a horizontal surface, the weight and the normal force are the same as well. So if I start out with my coefficient of friction formula, that would be the frictional force is equal to the coefficient times the normal force. I can go ahead and substitute in some numbers. My applied force and the friction were the same value, so I'm going to put my 14 newtons in over here. The coefficient is what we're looking for, and then the normal force would be the same magnitude or size as the weight of the object. And from here you should be able to divide, and notice that your units cancel out, and you're left with a coefficient of friction equal to 0.35. Remember that it does not have any units, and then also that number makes sense because it is between 0 and 1. Now there was a part B to the problem, and it asked you how much force you would need to apply if we stack some more weight on top of the original object. So we are looking for the applied force, and remember we're still keeping it moving at a constant velocity, so that means I can also look for the frictional force in that spot in my equation. And then we do have a new weight or gravitational force, which is also the same as the normal force now because it's still on a horizontal surface. So I can plug in that same number for the weight or the gravitational force as I would for the normal force. And then lastly, as a part of what we do know, I made you a note that the coefficient of friction does not change just because you add more weight. Remember, the coefficient of friction is a way to describe the texture of the surface. It's a way that we can see how rough or smooth it is. So just because I stack more weight on top doesn't mean that that texture changes. Remember that this is our formula. We can substitute in the applied force for the friction because it's moving at a constant velocity. Coefficient of friction doesn't change. And then my normal force would be the same value as my weight. So I'm going to go ahead and plug in those numbers. We found the coefficient of friction in part A, and we found a new weight by stacking the 20 newtons on top of the 40 that we already had. So when we multiply these two together, we should find that we need to apply 21 newtons to keep that block moving at a constant velocity. And just think, this answer does make sense because the block is heavier, so we should have to require more force to keep it moving. I'm going to have you pause the video and try to work this problem on your own, and then come back and I will show you the solution. First, you should have found the weight, and that gives you a value of 343 newtons, and I wrote you a note. This is also the normal force because we are not on an incline. Next, you want to find friction with our frictional formula using the coefficient. That gives us a value of 102.9 newtons. And then lastly, we're going to use Newton's second law to find the acceleration. The second law tells us that F net equals ma. Our net force was the applied force minus the friction because they are in opposite directions. You can use your free body diagram if you drew one of those. It looks similar to our first few problems. And so I plugged in those values, 155 newtons for our applied force minus the frictional force that we found equals ma. Solving for a, we find that we have an acceleration of 1.5 meters per second squared. Remember to go back, rewind, pause the video, do whatever you need to do to review the material, and then also if you would like individual help with these, please come in and I can work through the problems with you step by step to make sure that you know how to work them before we get to our test.